Now, yeah, all right, good. So I'm very pleased to be here on the occasion of David's birthday. The first interaction I had with David was actually when David sent a letter to Utrecht inviting Herman and me to come as postdocs to Princeton, because Herman had met you at Capri, I think, but I met David in Princeton for the first time. Now I've got to know you much more better the last number of years together with Maria, and well, we appreciate your friendship with Jackie and you very much. I have one little anecdote to say about the times we've been at Corsica. I remember also many things we did there, like swimming and so on, but also a conversation where somehow we got to discuss when you're just by yourself or you're just interacting with people and you don't see yourself in the mirror, what is the image you have of yourself of how old you are? Just your fixed time, age. And we were discussing, well, this is my age. And then David said, I always feel like this little boy who's waiting and cannot sit still and jumping and wants to play. And that's apparently what he always has been. And this is also an example for me of how you do physics. And I think you should keep that going for a long, long time. All right. So I'm going to talk about things I've been working on for the past years. This emergent gravity, certainly something that has been developing recently also very much. And so what I want to present is work that I'm going to be hopefully publishing very soon. And the relationship with the dark universe will become clear as I go along. I want to start simple. First of all, we all know sort of the Bekenstein-Hawking formula, but also it's teaching us something about, indeed, the relationship between space-time gravity and what I will call quantum information, in particular entangled quantum information. The Bekenstein-Hawking formula not just tells us about black hole horizons, but also about other type of horizons, and in particular also about the entanglement entropy even in empty space, in the vacuum. There's a lot of hints about how to think about emergent gravity, also coming from string theory, or what I call M theory, and of course ADS-CFT, and holography is then usually used in this context. Although I will have some things to say about how you should think about holography in this sort of more emergent gravity language from quantum information. So I'll start very simple and tell you a little bit about entangled quantum information by looking at the basic Bell pairs as being entangled pairs. There are very many ways you can entangle them, but there's 4 basis states which are maximally entangled. That means that one determines exactly the other one when you do a measurement. And these operators, these states, these 4 states, you can manipulate them by operators by acting either on the first spin, because you can flip the spin or change the signs, or on the second one. And this has a very important property, namely that when you have a qubit or amount of quantum information and you have it maximally entangled with something else, you basically control it. Because if I look at the bottom here, and I think I would like to have the pointer. Why doesn't it work? No pointer. Anyway, if I look at the bottom equation, you see you would like to change the state I, which is entangled with this other state, psi of I, then you can act with, am I doing this? Who was, you want to point for me? All right. So if I want to change the state I can want to act with an operator A on it. But I can get the same state by acting with an A, which actually acts on the second state. And so you control basically this qubit by entangling it. This is something you can also do with quantum information, namely store one important qubit in many other ones. And you hide it. And for instance, you can take one qubit hidden in 5 qubits, which is due to Shor, for instance, where you take a subspace of a tensor product of what I call physical qubits, and this is what you usually call the logical qubit, the one you want to be preserving. And now the nice thing is that if you have most of the entanglement with this, or most of the information, say 3 out of the 5, then you can reconstruct always the code. So the code space is only a two-dimensional subspace of a much larger one, but you can, by this trick, always recover it. And for instance, you can even generalize it where you have n of those physical qubits and I want to store k of them. You do this by making a subspace which is obtained by putting n minus k constraints on them, and then you can have hidden k into n. I'm going to use this to construct space-time because in a certain way what people are doing nowadays, a tensor network can be viewed as such an encoding mechanism. And Daniel, who's here, and his collaborators, well, I didn't write them all down, but Don Preskill, and there's recent papers by Patrick Hayden et al., who constructed these tensor networks as a way of constructing space-time. And the way to think about it is that in each node, each vertex of the network, you put a state with many indices, which are legs, that you can contract. I call them the physical ones, and they construct states, but by entangling them neighbor by neighbor, by basically projecting them onto contracting the indices alpha, say, for the neighboring points. So x and I are two neighboring points on the letters, and you can do it in higher dimensions even. And then you contract the indices, and this is how you build a network where all of the information, when every index is contracted, is only on the boundary. And you do this through entanglement. So anything that you do in the bulk, for instance, you can have one or several legs which are dangling, which means that you can act with operators here, but those are also entangled with the boundary. And what you need for this holographic codes to work is that they're maximally entangled, because then you control them. Namely, anything you do in the bulk, you can generate by acting on the boundary. And this is one way to think about holography in this language. And the nice thing is that you can even do holography at scales shorter than the ADS radius. But you have to have this property that the amount of information that you can put in this volume cannot exceed the number of legs that you have on the outside. So the connected tensors are maximally entangled, and it lives in the subspace, and you indeed want to have a number of dangling bulk legs, but they should be fewer than the Hilbert space that you have on the boundary. And that's an important restriction, otherwise the whole construction would break down. So here I say this again. So you have in a holographic error correcting code, it's called, you have dangling legs which are maximally entangled with the boundary legs, and you can map operators from the bulk to the boundary. And this is as long as the boundary entanglement has the majority. I said the majority sort of rules, but of course if there are more dangling legs in the middle which are active, you basically destroy the code. It sort of gets corrupted by the errors, and the holographic correspondence breaks down. So there's something about space-time that's somewhat fragile. You can namely heat it up. You can break the entanglement, and then suddenly a strange thing happens. So when there are too many bulk excitations, the bulk entropy may take over, and you don't have, well, if there's not too many, actually you have an area law. That means that you can cut the entanglement in this way, and you can count how many lines you cut, and this is what you have. And this actually allows you to indeed send information to the boundary. And one way I like to say it is that in the ground state, space-time is sort of a perfect conductor of quantum information. Any quantum information can be pushed to the boundary, and this is what explains holography. But bulk excitations should stay below the holographic bound, and if these excitations do occur, they thermalize. For instance, you can put excitations in the center, and then you have a black hole that you can create. But you can also do it more gradually, where you spread them over the volume. And they have indeed an entanglement entropy that grows like the volume, and eventually they may win from the area. Now the nice thing in anti-de Sitter space is that the area grows just as fast as the volume, and therefore anti-de Sitter space is the ideal place where you can sort of keep this going and indeed have bulk excitations as long as you stay within one ADS radius below this holographic bound. But what happens when the number of excitations win? That means I have more excitations in the center than I have at the boundary, and suddenly indeed the horizon forms at the boundary, and the excitations in the bulk, they win from the boundary. And this is what happens, as I will claim, in the Sitter space. So entanglement, first of all, you can think about this also in the quantum vacuum. So if I, as I said, look at horizons like winter horizons, you can write down the typical state that we recognize from the Undu and Hawking calculation, and there are many examples, and I am particularly interested in the de Sitter space, but you can also think about ADS-Rindler, ADS-Schwarzschild, and de Sitter, and they all have a causal Penrose diagram that looks the same, except that for ADS-Rindler you have the boundary here at infinity, but the horizon is this point here. This is what a black hole would look like, and then the horizon would also be there, and the boundary is here and this boundary. But in the Sitter space it's right the other way around. Actually the center would be this line, and the horizon is the one in the middle. And that's a very different situation. And here I draw a color in the sense that this is sort of a thermalized region which corresponds to a black hole. But I claim that even the Sitter space, because it has a horizon on the boundary, actually has a certain degree of thermalization, and therefore bulk excitations, which will be the dark energy that is added compared to the anti-de Sitter space. So there's this well-known first law of entanglement entropy, and this is how people derive Einstein gravity. They write down the Hamiltonian, the entanglement entropy, and they introduce what's called a modular Hamiltonian by writing the density matrix in the standard form of a thermal state, just like we had for the Rindler space. And indeed, the modular Hamiltonian is then interpreted as the boost generator in this direction, but it's defined in terms of the entanglement in this space. In a certain way you can think about this as therefore as a sort of an emergent time, because you define the Hamiltonian in terms of the density matrix. But the key identity that helps you to understand where linearized gravity, anyway, general relativity comes from, is this first law, where you consider variations of your density matrix, and then you can derive directly from the definition that there is this relationship between the change in the entanglement entropy and the expectation value of the modular Hamiltonian. And indeed it's like the first law of thermodynamics. And then you can show that general relativity derives when you assume that the entropy obeys an area law. And you can write, using the Wald formalism, some nice relationship between the entropy, which is on the horizon. In this case it would be in ADS-Rindler, it would be the horizon here. These are of course people that did important work with this. The Rie-Targanaghi prescription is being used here. Von Ramstonk, Myers, Cassini et al. They used this technique to derive Einstein's equations, because in order to show that the variation of the entropy on the boundary can be related to the energy change on the so the energy change, as we should say, on the boundary to the entropy change in the area law, you have to push indeed the integral from here, say from the horizon to the boundary, or in this picture it's from here in the middle to the boundary. And this is because you use some Stokes theorem. And this is exactly reflecting the fact that in ADS we can push things from the bulk to the boundary, and indeed the area law tells us that we are precisely in a situation where information is being sort of conducted from the center out to the boundary. And therefore general relativity basically presumes an area law for entanglement, and space-time is in this perfect information conductor phase, and all information is being pushed to the boundary. This may not be the case when we are in de Sitter. Let me now, this is sort of vacuum Einstein equations, and maybe with some waves on it, but let me introduce also how you think about matter being added. And here I'm making a statement about how you measure mass in gravity. You put a mass in the center, and one way we can measure it is called the ADM mass. I'll write down an expression later, but has to be, you can interpret this basically that matter is being entangled also with the boundary, but it's therefore removing part of the area. And you can think about, in 2+1 dimensions we have angle deficits, but in higher dimensions you can think about the mass as creating an area deficit. And this is indeed a formula for the mass. If you measure the increase of the mass, the area, as a function of the geodesic distance, and you take the difference with the vacuum, then you get something that's exactly linear in the mass, and that's actually a way of defining the mass in terms of basically the fact that Newton's potential enters in the geodesic distance. So mass is related to a reduction in the area, and this suggests that indeed inertia, or whatever the mass definition, is related to the entanglement of the mass with infinity. That's how I interpret this. This happens in flat space-time and in ADS, but What we are interested in now is actually eventually the zeta space. And here we have kind of a different situation. So here I'm assuming a universe that has only dark energy in it, so I'm not going to add any other matter. And the zeta space has the familiar metric, where L is the de Sitter scale, and I'm going to actually introduce other quantities later on that are related to the scale L. There's the Hubble constant, but there's also the acceleration scale, which is the acceleration at the cosmological horizon, and that sets the Gibbons-Hawking temperature. So here we have quite a different situation, because indeed the horizon is at the boundary and we don't have an infinity to work with, for instance, and there's no boundary like in anti-de Sitter space. So how does one define mass in the Sitter space, since there's no asymptotic infinity? So here's the causal diagram, and I imagine putting matter in the center, and I'm going to think about how to measure mass, because I said you can measure it in terms of the ADM definition, and this is usually where you integrate at infinity. So this is an expression that is explicitly written down in terms of the metric which you might have at asymptotic infinity for the ADM mass, but here we don't really know what to do. But however, I expect that when I go into some distance away from the mass, far enough that the mass is not very important, I'm in weak gravity, and here the horizon is still far away, that this expression is approximately true. But what I'm also interested in, what really happens to this when I push this again to the boundary, because to the horizon I should say, because it's not really a boundary, and this is where I have a thermalized region, and I do expect that all of the discussions I had about well, the thermalization and even the excitations start to play a role here, because these excitations that are present in the Sitter space are changing the entanglement structure and basically break down the area law that we have here, and we have a different space-time filled with excitations. So this is going to change the way we have to derive gravity, because we cannot assume the area law anymore. One other nice calculation you can do is that when you put a mass in the center, you actually change the location of the horizon. It's a sort of standard calculation. You add the Newton's potential to the equation that defines the horizon, and since the Newton potential has this familiar form, you can calculate by how much the R changes where the horizon should be. It's a little shift, I call it U. I'm going to actually relate it later to a displacement, but it's a displacement that's determined by Newton's potential at the horizon and the acceleration scale, because if Newton's potential is divided by an acceleration scale, it's actually displacement, and it's precisely this displacement that we have here, because if I now calculate the change in the area, it looks like the first law, except the area decreases, and this is indeed 1 over the temperature, and this is the energy. So the area is decreased, and actually you would say that that means that entropy is being taken out of the Sitter space when I add a mass. And I'm going to think indeed about, and this is a very important statement now, that the Sitter space is an excited state, and you can almost think about it as an excited state of ADS. Here I wrote down the metric again, but I wrote it like it's an ADS space plus some excitation energy. And the excitation energy is the excitation you add on top of the anti-de Sitter space with the same radius. And this is sort of the excitations that are occupying the bulk, and they break the entanglement in such a way that there is an entanglement entropy already in the bulk present that wins it from the entanglement across the boundary. And this is sort of what you should think about, that when you're in the ground state, the network is really just one nice state which is 0 entropy, but you can have entropy in a system that looks very similar, but it's what's called the glassy state, which has many possibilities, but it has an entropy density that's simply spread over the entire volume. This is going to change indeed now the way I'm going to think about the derivation of gravity, because now I'm not just changing the area law, I have to keep track of this volume contribution to the entropy, which is associated to the excitations in the dark energy. Another way of saying it is EPR is ER, which is namely, well, here I didn't have a picture for the cosmological horizon. This is what Lenny Susskind and Juan Maldacena had for black holes, where you think about the horizon not as something being entangled with the other side with wormhole, but there's sort of the entanglement is actually with the stuff that's already on the outside, which in the Sitter space would be the stuff inside. So there's a certain self-entanglement happening around the horizon where you are thermalizing the degrees of freedom of the space-time. So now I'm going to write down my assumptions. I'm going to indeed say gravity emerges from entanglement entropy and using sort of a first law. And that gravity, I mean general relativity, actually requires entanglement to obey this area law. And it's only true, by the way, in ground states which are gapped. And generally when you have excitations, this is not a true statement that there's an area. So general relativity is actually kind of special. The Sitter space, that's another assumption, is actually an ensemble of excited states with a finite entropy, density even, and a temperature associated to the horizon. But I'm going to apply the same principles of emergent gravity, and I just need to generalize them with including a thermal entropy density. And we'll see this is going to lead to something which is very similar to elasticity of the space-time. No, we have to know exactly what the energy is. So here I've written down the region inside one ADS radius, and I've excited the states, and here you actually are making use of the fact that you can indeed fractionalize your qubits in the sense that there's the information sort of over the entire volume, but I put in just enough energy so that at the moment that I reach the ADS radius, this is where I'm reaching the horizon. So I'm thermalizing the state from the inside. And here I break the entanglement with the outside. Of course, no, there's a horizon. It's the de Sitter horizon. Sorry? Firewall. I draw you the picture. I mean, there's nothing behind the horizon. You entangle back. That's true. So I'm not adding ordinary matter. I'm exciting degrees of freedom. And actually, there's one way there's a longer story here which I cannot tell you. I should discuss this later. But this is actually the statement that indeed in the bulk you can think about a region in here as carrying part of the information that's associated to the boundary by simply spreading the qubits over. So this is your code space, your physical Hilbert space. This is the amount of information you put in there. It's not living on the boundary, it's living everywhere. I'm not trying to do this. I'm thinking about the Sitter space in a certain way.
Can you say what you're doing on the gravity side?
I'm considering the Sitter space.
But you're starting from ADS to get the Sitter space requires more than this.
I wrote it here. This is what I'm doing, not more. If I plug this in here, I'm just rewriting the Sitter space. That's all what I did in From 0 to L, this is the Sitter space. Plug this in here, put it in there, and it's the Sitter space.
Are you saying you're going to the question, or are you confirming that?
I think I'm giving you a way to think about the Sitter space once you understand some things about anti-de Sitter space. And the whole story that I said in the beginning should convince you there's some way in which the entanglement is broken there by the thermalization of the bulk. That's the only statement I want to make. And I'm not going to use very much about what's in the bulk, except that there's an entropy density. There's very little I'm going to use about this. So I'm going to actually continue with thinking about the Sitter space. So I'm introducing the Sitter's radius acceleration scale related to the Sitter radius. And I'm going to define something called the surface mass density. It's namely just the mass being spread out over the area. So I think about this in terms of the acceleration. If you divide it by 4 pi g, just like you do for electromagnetism, you get the mass divided by the area, and this is the surface mass density. And there's a very important fact about the critical value of this, which I call it. There is a certain surface mass density. When you go below a value determined by A0, this is where you will see things like dark matter appearing, or what I will call the missing mass problem, because it's where the nature of gravity changes. And this is an important hint, because you can rewrite this as this is the change of the entropy of the de Sitter space, and this is the area of the surface of the sphere I'm making here. If this is smaller than that, then something changes, and actually you can interpret this as follows. This equation you can write actually when I calculate the entropy that the mass takes out of the vacuum, and I calculate how much entropy would be in the Sitter space in the same volume. This actually becomes below it, but actually when it's above it, that's where we are in the normal gravity regime, but when it's below it, we actually see deviations. So I'm going to calculate these deviations and see what I get there. Same statement again. So this is the change in the area, and I'm going to think about not just changing the area of the horizon, but also thinking the volume is being changed. Indeed, I'm thinking about that matter actually removes part of the entropy that's in the volume, and the response will be like an elastic one, because instead of calculating differences in areas with area deficits, now I have volume deficits, and this is a familiar theory. It's actually 19th century physics. It's elasticity. So let me observe something about the ADM mass expression. So this is the ADM mass, and if I write down the asymptotic metric as if I'm still in sort of asymptotically flat space, I can write it asymptotically in terms of Newton's potential, and n is sort of the normal vector pointing outwards or in radial direction. You can write down the ADM mass in a very suggestive way in terms of what I call a strain tensor, which is defined in terms of this displacement vector, which is in the same displacement one I actually found in the elastic response. And this is actually something which you can recognize almost as being, well, this is the integral that would be a normal direction on the surface. Actually, this is what you in elasticity if you computed the traction or the force on the boundary of it. And indeed, there's a relationship between the mass, ADM mass, and these elastic equations. This, by the way, is just a rewriting of the normal equation when I put in this metric. I don't assume anything, it's just simple math that this is possible. But I'm going to indeed extend this equation. This is the central reasoning. Space-time geometry represents an entanglement structure of the underlying quantum state, and matter changes the entanglement structure and hence introduces area deficits. That's what we call curved space-time. When we have dark energy, we have bulk excitations that carry a total entropy equal to the de Sitter horizon. And matter not only changes, therefore, sort of the architecture, which is sort of the entanglement structure which we have here, but it also moves around the information that's stored in it. This creates a back reaction. It's sort of the extra elastic response that's responsible for what we see in de Sitter space-time. And I can calculate this. Namely, if I have a point mass that changes the displacement of an elastic minimum, it experiences a force. So if I think about the displacement factor as being representing by how much I'm displacing the information in the dark energy or if in the de Sitter space, if I do this, I create a force. Namely, if there's a stress tensor and a strain tensor, which in the usual way are related, this expression holds. And where the integral is just around surrounding the point mass. And there's a conservation law for the stress energy tensor, just like in textbooks. This is very analogous to what we have in gravity. Here I define a similar equation for the gravitational force. And I'm actually going to relate those two equations because I'm going to interpret this force as a dark component to the ordinary gravity. And the relationships are very easy. Namely, if I write down my same correspondence I had before, I insert this in the first equation, and then I read off something that would look like the second equation, how I can determine from the stress in the system, the stress tensor, the surface mass density, which is the same vector which I have here. Because when I insert this one in here, you see very easily that when the inner product of n with the sigma is equal to this capital sigma, then I get this relationship. And this equation works very nicely. And I don't need to do much now. Actually, I'm going to derive an equation for what sigma is and determine the force from that. It's a standard textbook calculation. I'm calculating how much volume is being removed. I have the equation for u in terms of phi. I have a strain tensor, which if you square it, you can integrate it. And this is just standard equations where I assume this to be conserved. This actually you can show, by the way. I just summarized here the step because I think I already written down for you to explain the basic ideas, which is this one. Yes, I'm going to be done in 5 minutes. I actually have a relationship between the square of the strain and the replaced volume, and this displaced volume will be proportional to the mass in the system. This is going to determine the acceleration. And this is basically the equations again. This indeed is the volume, and this is a relationship which I had before, which is that this is actually the elastic energy in the volume related to the volume, to the displaced volume due to matter. I'm going to actually skip this. I'm actually going to indeed go to the main. Well, this is indeed not the equation I wanted to have here. Yeah, actually, let it. The equation I can derive in this way is this equation. There's a relationship between the surface mass density, which you get out of the elasticity. I showed you the square of the strain and related it to the mass. And this is the surface mass density of ordinary matter. If you work out the numerology, actually, you find that this is 1 over d minus 1, and this is, in our dimensions, it's 1 over 3. This relationship actually translates to this relationship where this is the Mond acceleration parameter with a 1 over 6 in it. It actually comes from our dimensions, space dimensions. And these are the observations. There's really a way to get these equations out of the reasoning that I showed you, out of the elasticity. And so this is maybe even where I want to finish, in the sense that I know that when I just continue the the steps I showed you, there's actually a way of deriving a relationship between the acceleration and the mass in the system. Let me indeed show you what some of the plots I get. This is actually a relationship you get in terms of densities, in terms of the baryonic mass and the dark matter mass distribution. When you simply assume that each of these masses are this, these are the average densities defined in the mass in terms of the integrated mass to a radius r. You divide it by the volume, you get the average density. These relationships can be matched with data like this. This is in clusters. This is from a paper that discusses those distributions. This is what I calculate using the formulas for the Cloma cluster. And this is what I get even for the dark matter density. So this is a formula that works magically well and actually has a derivation from the logic I gave you. This is with happy birthday. No. They're gonna turn up empty.
And you get the efficient curve.
Yes.
What happens to something like
So I don't read. So what I have is an effect, which is this elastic effect, and I estimated its magnitude using certain assumptions, and this is actually called a memory effect calculation, which assumes that things are not dynamically changing very fast. And so if there is a dynamical situation, you really have to solve different equations. I'm not writing down a law, like Milgram said, that I say has to hold in all times. I'm giving you a physical picture, then I'm estimating it and can reproduce those laws that have been observed. But it's a very different way of arriving at it. And so there will be situations where these assumptions that I made might be maybe broken down. And actually,
so if you're saying, and then a theoretical test
so what is most important for that is the excess gravity you have on top of the normal one. You want to create a well. And that well here is being also there because I have an excess in gravity. And it's actually caused also by the same mechanism that makes the matter appear. Because I think about even the volume being removed from the dark energy as a step where the matter has somehow starts to the contraction that happens when we do gravitational collapse is actually related to that same phenomena. So I think there are ways you can probably use similar reasonings as for structure formations were necessary based on this kind of extra gravity you get. But anyway, I didn't solve any dynamical issues. I looked at these equations from this perspective. Maybe Tom, yeah. I know exactly what they do. I know what they do. I know exactly what they do. They want to reproduce something based on that paradigm that looks like the real world, and so they give themselves all kinds of knobs, like how quickly the star forms, how many supernova are here, and then they turn their knobs, and then they are happy when something happens that looks like the real world. And they do the same thing when they do every galaxy with the same number. They have 3 parameters that they adjust for every galaxy independently. This is a theory without any free parameters. Because I haven't solved the dynamical questions. I think Elias was actually first. So, nee,
various theories, standard theories of God. In fact, I'm not trouble accommodating, for example, people in philosophy and stuff like that. But they have trouble eventually accommodating it to the which eventually brings the question, do you have any idea how to derive quantification theory?
Let me. I showed you curves, which is quite quantitative, which reproduce data at distances, say from a few kiloparsecs to megaparsecs. That's something that's being skipped when you go to this other theory, which assumes general relativity and then goes on. I think there's ways you will have to eventually put those things together, and it's true that the early universe story has to be sort of, and the whole dynamics of those questions have to be studied in this picture, but it's not like I think that is impossible. But I feel that there is issues about gravity that have already need to be addressed at shorter distance scales than the cosmological ones. And that's basically the dark matter phenomena. And assuming that is solved and just going up to all the other scales and extrapolating everything back to the early universe, I think may have made based on assumptions that I'm not always very happy to assume. I think, anyhow, there's a chairman here, I'm continuing here.
How do you manage the fact that when you embed your de Sitter space, that actually the de Sitter space effect is just the static patch, and that means that this is also dependent.
That's correct.
How do you manage?
I have a paper on that even, where I know how to patch together when you go from different patches. But the crucial thing is that when you are in the middle of your own universe, you don't need to talk about what's behind the horizon, and that.
Except if you say something about inflation or in that region, then
Same story there. I mean, it's not something I considered. I think I looked at the static patch, and it's within one horizon. And certainly, if you think about complementarity or even the EPR's ER picture, you don't talk about what's behind the horizon. You simply don't. Yeah.
Well, I'm really still stuck on the same question at a more technical level. How say you go to ADS?
This was, no, sorry, I really want to emphasize, that was a way of explaining of how I do the Sitter space. It was not something how I derive the Sitter space. So if you don't accept the explanation, forget that I said it. I do the Sitter space. That's the point. And then I gave you an intuition about it, and you don't accept the intuition. Fine. There, so okay, maybe let me then indeed explain. ADS-CFT is capable of describing anti-de Sitter space at scales larger than the ADS radius. It has no information about anything shorter than the ADS radius. In order to do so, you have to go to sub-ADS scales, which introduces additional information in the bulk which the CFT doesn't have. The CFT has namely n squared degrees of freedom for every radius, and it doesn't have anything more. And therefore, understanding ADS at sub-ADS scale is just as difficult as understanding de Sitter space. No, it has thrown away even in the construction of ADS space, of ADS CFT. We go to the infrared, we have done a decoupling limit, and it's really an infrared description even of the bulk. So there is no information at sub-ADS radius scales. So if you do Ryuto Kenyaki, what you're doing, you're taking a curve from the boundary and you're counting how many ADS radii you're going through, because the ADS radius is the cutoff in the theory. Anyway, we should probably stop this anyway. Anyway, all right.